Hello and welcome to this clip on chromatography to A2 level. We'll go through the basic idea of chromatography being a technique used for separation of individual components from mixtures of substances, how this separation takes place as a result of each component's preferential attraction to either the mobile or stationary phase via intermolecular forces, and the application of this idea through thin layer chromatography and through gas chromatography. And it's assumed throughout that you're already comfortable with how intermolecular forces work from your first year of A-level chemistry. So chromatography involves the separation of mixtures, and the simplest type of chromatography is called thin layer chromatography. So a thin layer of silica is attached to a small sheet of plastic, and the sample mixture moves up carried by a solvent. So different components in the mixture are carried up the plate to different amounts, and this depends on their attraction for the stationary phase or the mobile phase. In this animation, and in TLC obviously, the solvent will be the mobile phase because it moves up the TLC plate, and the silica in the TLC plate will be the stationary phase. And like we mentioned in the introductory slide, it's down to intermolecular forces between the individual components of the mixture and each phase. So thin layer chromatography works by adsorption onto the stationary phase. The stationary phase will be some silica bonded onto a plastic backing, and it will be cut into small pieces, roughly about the size of what you have on the screen, and they can be dipped into a solvent, and the solvent is the mobile phase that moves up the TLC plate. So if you imagine the black arrow representing the solvent moving from left to right, what happens is each of the dots in different colours represents the components that are in the mixture in the diagram that shows the 4 TLC plates. So you can see clearly that the blue component doesn't really adsorb onto the stationary phase. It moves along, and by contrast the pink component does attach or absorb onto the stationary phase. The green component absorbs onto the stationary phase even more. So therefore the green component moves the least amount up the TLC plate. So as the components begin their journey, they're carried by the solvent. So the solvent is the mobile phase. And they start to separate depending on their attraction for the mobile phase or their tendency to absorb onto the stationary phase. So this is all dictated by intermolecular forces, don't forget. So each component will have different intermolecular forces that its molecules will exhibit. And those intermolecular forces might cause greater attraction onto the mobile phase, or they might cause greater attraction onto the stationary phase. So the illustration at the bottom of the page attempts to replicate what's going on in the image that's on the screen. So basically, by the time you get to the end of the chromatogram, in other words, the process has happened, and the chromatogram is the TLC plate with the separated components on it, you can see quite clearly that the pink and green components have adsorbed onto the stationary phase more effectively than the blue component, which has continued to travel with the solvent up towards the end. So at all times, the front end of where the solvent is called the solvent front. So this represents the front boundary of where the solvent has travelled to up the plate. And it's a really, really important distinction that has to be made here, that it's adsorption, not absorption. Loads of people make the mistake of calling it absorption, knowing what they're meaning or trying to say, but inadvertently saying that absorption has taken place. That gets no marks at all because it's not absorption. Absorption would be if the component got absorbed into the silica. It doesn't. It gets adsorbed onto the surface of the silica by intermolecular forces. So it's really important to make sure that you don't get that confused. before you go any further. So here's a simple example. Maybe the separation of the pigments in leaves might be a good application. So the process is carried out in a glass tank and the lid stops the solvent evaporating. When the solvent front has visibly reached the top of the TLC plate, your chromatogram is ready to take out. So this is a very simple technique. It can take maybe 15 minutes, it might take 5 minutes. It depends entirely on the solvent that's chosen. So the actual solvent might be a pure substance or a mixture of substances depending on the components you wish to separate. And a word of warning, if you're doing this and you have to choose the solvent, you have to choose carefully because the components might not actually separate. If the components have equal attraction for the solvent, they'll simply just travel up together and not separate out like the photograph has shown. So chemists have to choose the solvents very carefully to match the components that they're actually trying to separate out, otherwise the process doesn't work. So the retention factor is a measure of the extent to which the component dissolves in the solvent. So it's essentially a ratio of the distance moved by the component as opposed to the distance moved by the solvent front. And as you can see, this value differs from the three different components being looked at in this diagram. You've got a blue component, a pink component, and a green component. So the larger the RF value, the further the component has been moved by the solvent. The smaller the RF value, the less the component has been moved by the solvent, and the more it's attracted to the stationary phase. So gas chromatography involves a liquid stationary phase on a solid support, as you can see from the diagram at the bottom left of the screen. There's a carrier gas that brings the mixture through the capillary column. It's injected into an oven inside which the capillary column sits, and the detector is connected to a data system or recorder. So what happens here is you get something called retention time, and the retention time is plotted on a graph called a chromatogram. The next slide will talk about what a chromatogram looks like, but what's happening here is the stationary phase is liquid, and the gas will actually carry the mixture, which will be heated so it is a gas itself, so the individual components will be gases. So the carrier gas will move them through the capillary column, and to different degrees each individual gas in the mixture will be attracted to the stationary phase, which itself would be liquid. So the more that the gas is attracted to the stationary phase, the more it's slowed down, and the longer it takes to move through the column. The less that the gas in the mixture is attracted to the stationary phase, the more quickly it can move through the mixture. So the retention time is the time taken for it to move through the column, and this will be specific for each of the individual components in the gas mixture. So what you get at the end of this process printed out is a gas chromatogram. This will have a series of peaks on it. So we have component A, B and C in our mixture, and the retention time is measured in minutes along the x-axis and represents the time a component spent in the column from injection to detection. In other words, on the diagram, the time spent here. And this in itself, at this time, will be dependent on the component's solubility in the liquid stationary phase that's shown in that diagram above within the column. So a short retention time will be low solubility in the stationary phase and a tendency to move through the column quickly along with the carrier gas. A long retention time will mean there's high solubility of that component in the stationary phase, and it'll tend to take longer to move through. So looking at the peaks for A, B and C, it's clear that A has the shortest retention time. It also has the largest area under its peak, so it therefore has the largest proportion in the mixture. B and C will have different retention times, but their peak areas are fairly similar, so they'll have similar proportions in the mixture. So the proportion of a component in the mixture is equivalent to its concentration. And if we approximate the area under a peak to concentration, we can do a calibration curve for a substance within a mixture. Now the concentration can be measured in micrograms per litre, but what we're doing in the first step is to put several different concentrations of the known substance through the GC and record the peak areas. So we're not looking at the mixture just yet. What we're doing is looking at what peak area we get when we put a known concentration of the known substance through the gas chromatography machine. So if we run a chromatogram of the mixture, but what we've done is plotted a graph of all the different concentrations against the relative peak areas. So in other words, on the right hand side, bottom right, is the calibration curve. So you can see it's a straight line with the concentrations 40, 60, 80 and 100 micrograms per litre along the x-axis, and the corresponding relative peak areas along the y-axis. So let's say we want to find out what the concentration of our component is, and we decide that our component represents this peak here. All we have to do is to look at the peak area on the calibration curve. So let's say the peak area is there. That gives us the concentration. So in this way, gas chromatography can be a quantitative measure of a mixture as well as telling you relative proportions. It can give you exact concentrations as well. So obviously that curve can be used to work out the concentration for any peak area. So for example, if we wanted to look at one of the other peak areas, let's now just highlight that. Let's look at this one here. That'll be a lower peak area. So that one might be elsewhere on the calibration curve. So anywhere along that line can be used as a way of working out the concentration. So it doesn't really matter which type of chromatography you're talking about, it'll be based on intermolecular forces. In gas chromatography, it'll be separation by relative solubility, and in thin layer chromatography, it'll be separation by adsorption. So it might be worth pausing the video and getting these two diagrams on this screen down, because they're a good way of memorizing the two different, slightly different ways of separation that you get in the two techniques. So let's now have a look at an exam question. It gives you some information with the diagram, and the rose oil that is extracted by the separation apparatus can be separated into its components using TLC, and it gives you a chromatogram, and it shows clearly that you've got component A, component B and component C. And what they want to do, well, what they want you to do, is to explain how TLC separates compounds in the mixture, and that will be via adsorption onto the stationary phase. It's important that you don't confuse this with absorption. Absorption, A-B-S-O-R-P-T-I-O-N, absorption would be if the component got soaked into the stationary phase somehow. That doesn't happen, it gets adsorbed onto the stationary phase's surface via intermolecular forces. Important to distinguish between those two processes and to not get confused. So the RF value would be estimated by actually measuring x and y as distances, and dividing x over y. So to estimate the RF value, what you do is on the script you'd measure x in centimetres and y in centimetres, and then divide x by y. You do this obviously using a ruler sitting there with the exam in front of you. This is obviously a scan of the paper, and it's maybe slightly bigger in scale than the actual paper itself, so I'm not going to measure it, because it might not match up with what's going to come up in the mark scheme. But the way you do it would be to measure x and then to measure y and divide one by the other to get the retention factor. So the next question asks you to use the chromatogram that was on the previous slide. If you recall, it only had three spots. And unfortunately, if you get a situation where 2 or 3 compounds have the same retention factor, that means they travel up together and don't get separated by that particular component. You can't automatically say via TLC that you have 3 components if you get 3 spots. One of the spots might still contain 2 or more compounds. So then it asks you to identify, it says GCMS was used to identify the compounds present in the rose oil, and you've got the structures of them given on the page. And it asks you to explain how GCMS can be used to identify these compounds in the rose oil. Now you remember that MS would stand for mass spectroscopy. I didn't mention that in this clip, but obviously gas chromatography and mass spectroscopy often go together. So you start off by separating using gas chromatography, and then the mass spectrum is compared to a database that the mass spectrometer will have built into its program. So it's important not to imply in your answer that mass spectroscopy on its own can identify a compound. It can't. Mass spectroscopy only gives certain information such as the MR or maybe its fragmentation by comparison with a database like I mentioned. If you fall into the trap of saying mass spectroscopy gives an identification of the compound, what you're doing essentially is ignoring the fact that infrared spectroscopy can give information about a compound and NMR spectroscopy can give information about a compound. So together they'd identify a compound, but GC just separates, and then MS gives information about fragmentation by comparison to a database. So to answer the next part, which says suggest with a reason which 2 compounds might be present in B in figure 5.1, I've reproduced figure 5.1, and it's quite clear that B is more of a smudge than a spot. So that suggests there might be more than one compound present in spot B. In addition, the fact that they're travelling up together, not separating out, must mean they have similar retention factors, which means they have similar properties, which means they'll have similar functional groups. So that makes me think that it would be nerol and geraniol, because not only are they stereoisomers of each other, they're also primary alcohols, and so as such will have similar degrees of intermolecular forces attracting them to the solvent. So therefore they'll tend to move up together. That particular question is actually quite difficult and really does poke and prod at your understanding of what's going on in terms of intermolecular forces. So just to recap on that question, B, or spot B, is more of a smudge. So therefore it's more than likely to contain more than one compound. Point number 1. The choices that we have from nerol, citral, geraniol and menthol is most likely to be nerol and geraniol because they're similar to each other, and what's most important is they've got the same functional group, primary alcohol. So therefore primary alcohol is likely to behave in a similar manner towards the solvent and therefore be carried up to a similar extent by the solvent, and as such will have a similar retention factor. So the next part asks us to explain what's meant by the term stereoisomerism or stereoisomers. So stereoisomerism or stereoisomers means the same structural formula but different arrangements of atoms in space. Both of those points are required to get the single mark. So just to check the mark scheme, we talked about adsorption, and look at what they say. Do not allow anything that begins with ab, or absorption is absolutely not allowed. Now the 0.2 value, that would be from the actual measuring that you do on the script with the piece of paper in front of you. But you can see that they're quite flexible because they allow between 0.1 and 0.3. We said that the spots will contain more than one compound. We talked about GC doing separation and mass spectrometry being used to compare to a database or reference, so that both of those points were allowed. We chose neural and geranial, and we mentioned that the stereoisomers and the fact that they have similar functional groups, e.g. primary alcohols. We also said that stereoisomers have the same structural formula and different arrangements in space. We didn't do the part on chirality. I left that one out because this particular video clip is not about chirality, but the question went on to talk about chirality. So I left that one out on purpose. So hopefully it's been a fairly useful little clip to take you through the basics of the theory behind chromatography and the two main types that will come up in your exam, and a few of the pitfalls and the ways in which they test you out as well. So if you have any queries, obviously bring them to one of us at a subject extension at college, or maybe have a chat to your teacher. But in the meantime, thanks for your time, and see you soon.